next speaker is Mark Burchell, University of Kent. Cometary delivery of volatiles to the moon. What can we learn in the laboratory?
Okay, thanks. Well, thank you, and thank you for all staying to the end of the Friday afternoon. Mine is a more gentle talk, perhaps, because it's built around really the change of a paradigm over the last decade, and about the fact that we now need to understand a new situation, so we need to get back to the laboratory to do some more experiments to update our knowledge. So what we have is an object we all know very well, which is the moon. And you might think that all that we can do with the moon is take higher resolution images of the moon. And so the images are indeed getting to be higher and higher resolution. You can pick your favorite features. You can go to the libraries these days and look at them in great detail. But of course, more is happening than that. And here is just, for example, from the LRO from NASA. If you look at the moon at the North Pole, you can now see in extraordinary detail. You can, by the way, you can zoom into this map and expand the region you want. And you can start to see, in this case, some of the famous deep craters, which, due to the obliquity and the illumination from the sun, there are craters on both the moon and Mercury where we should have permanently shadowed material, which I'll get back to later. But so we can see some of these nice features now in great detail, which we've sort of known about. But is that it? And of course the answer is no, because as we learn more, we change what we thought we knew. And so here is an older map of the moon. This is one of the sort of ones that the Apollo era people like me who grew up looking at all these maps, putting them up on your wall, these were the sorts of colours the maps had. And if we ignore for a moment the orbit of the Grail spacecraft on their final orbits during their controlled descent, we can see the classic dots showing the various sites on the near side of the moon where the now famous Russian, or so say Soviet in that era, and of course the American Surveyor and finally Apollo missions were landing. And you can see, we've already heard how you choose landing sites. I suspect it was a little bit more relaxed in those days, but there were still constraints. We're on the near side, we're forming a band across the surface. And of course, from a few of those sites, both the American and the Russian samples were returned. So when people talk about finally having a sample return mission from Mars, of course the Russians will all tell you, well, we did that decades ago with the moon. Just catch up with us, will you? But it does mean that we have more than just the Apollo sites. We've also got some of the other sites which return material to the Earth. So why are we still talking about the moon? After all, we have been there, as I just pointed out. We've even brought samples back from known locations. So therefore, haven't we done it? And the answer is no. It's still full of surprises. And one of the surprises that I still find people are surprised about, is just how many lunar missions there have been in the recent years. And so we'll look at that in a minute. They have simply become much more frequent. Some of them are technology testing, because it's a convenient place to test new technology. But also there's science built in, and that is changing bit by bit what we understand. And of course there is the continual, depending to answer an earlier question, arrival of the cavalry, or a threat, if you think robotics is the answer, that sooner or later there will be astronauts back on the moon. It's always 10 years away. So when I say within a decade, maybe 5 years' time, we'll still be saying in a decade. But sooner or later, it's almost certain that people will be back, and we'll find out the answer then, which is better, rovers or people. But if we just think about those old missions for a moment, as I said, there's Soviet and there's the American NASA ones, but it is astonishing. There were over 60 missions in what was really a very tightly constrained period of time of just about 17 years. And they started with the simple flybys, which showed the first images of the far side of the moon, which, of course, were a great British discovery if you read the books, because Jodrell Bank, listening in, was showing us the images before the Russians released them, I gather. It's a cheap way to do science, but I'm sure there are people who can tell us the full story of what went on. But as they became more sophisticated, as well as the orbiters, there are the landers, there were the astronauts with their high level of mobility concentrated in short periods of time, whereas, of course, the rovers we all know and love today aren't actually going very far, and they're taking a long time to do it. So they are slow but certain, but they are limited to how far they can go. And so one thing about the moon is we did have the sample return, and we had The rovers, some of which were with astronauts, and some, of course, were without astronauts. But then nothing at all for a long period of time, because, of course, we learnt it all. We hadn't, but there we are. But when you add them up, since 1990, there have now been 14 lunar missions, 10 in the last 11 years. So that's almost a mission a year. So it should be no surprise that the sheer accumulation of results is changing our picture of the moon quite significantly. Now, as I said, some of these missions were primarily technological. The European Space Agency's Smart 1 mission, of course, was demonstrating that you could use electric propulsion to get around, but it also has science on it. There are mostly orbiters, but there have been landers again. We've got the example of the Chang'e lander with its jade rabbit just recently on the lunar surface. And we've had impactors with L-Cross. NASA, of course, as well as LRO, has le.g in a very low orbit around the moon. So it's convenient we're talking this month because it's not going to be orbiting much longer. There should be a controlled descent into the moon come the end of this month. But I'd say on the quiet, the message is it should be no surprise, given the number of missions, that lunar science is changing. Here, for example, is the traditional artist's impression of what le.g looks like as it orbits the moon. And just to emphasize that it is an artist's impression, but it's also carrying instruments. It's trying to measure exoatmospheres, and it has a neutral mass spectrometer. It's trying to see, is there any moisture in that atmosphere? And there was a spike after the Geminid shower recently. Now, unfortunately, also almost coincided in time with Chinese activity on the moon, so you have to try and separate in time. But we do appear to be seeing how material is being delivered to the moon and how it's influencing the environment around the moon. And this is a very recent result, so I can't even cite the paper because it's the sort of thing that's still hearing of in conferences. It's not my result, I won't claim credit for it, but it is showing us we are thinking about delivery to the moon and what happens to the material when it gets there. Here, by the way, is something I found while I was making the talk. This is apparently is le.g seen from LRO. So there's now multiple spacecraft around the moon and imaging each other. And I have stared at this, trying to spot where is le.g. I think it might be that little blip there. It sort of matches the general shape. And le.g is supposed to be in a low orbit. But it does make the point. There are now multiple spacecraft active simultaneously around the moon. There are more proposed missions. I've not mentioned the private providers on this list who are racing to win. Usually they're spending 50 million to win 10 million. This is good economics in the space race. But here I've just listed some of the ones we're maybe not quite so familiar with. The Chinese have got a continuing program where they promised a rover next year. And then if we go a bit forward, a continuing program, I'm not quite sure they'll achieve sample return then, but the Chinese tell you they have an impressive track record of delivering what they say. Perhaps less impressive is the Russian track record in recent decades. Something's gone wrong with the grand Russian armada of planetary spacecraft. If you've worked, like I did, on Mars 94, which became Mars 96, which really became Pacific/Chile 96, you might be a bit worried. And also then with some people like John Bridges, we were very excited about Phobos Grant a year or two ago, and of course that also had its problems. So something is happening. The Russians can launch, by the way, commercial satellites. They just can't launch a government-owned, government priority vehicle for some reason. But they have promised penetrometers to get into the moon, and that will help us probe the moon interior. And I was looking through exciting images to put in this talk about the interior of the moon, and I just couldn't find anything which didn't look like it had been hand-drawn. And we're still relying, basically, on Apollo-era data, a lot of which was very ambiguous. So trying to get some interior data from penetrometers and listening afterwards to just the seismometers, that will be useful. India, of course, has promised Chandrayaan-2. They will tell you it was delayed because they had thought they were going to work with the Russians. But it's very expensive, and it's very difficult to get a lander and a rover, so whether they'll achieve it on that timescale, we'll wait and see. China, of course, I've mentioned, and then Russia has been promising for a long time this large rover, but it's already been delayed. But we should expect to see a lot more on the moon with some limited surface mobility and some subsurface data, whether it's mass spectrometers in the subsurface or, more importantly, seismometers. And, of course, the famous manned missions. NASA is now promising a flyby, and the data is already slipping. Not they're going to land, it's just that they built Orion. And if you believe the budget statements, they have to go somewhere. They're not actually going to land, they're just going to fly by. India had promised in this decade, but that's gone, I should imagine, and China is now saying 2025. But don't forget the Chinese are in Earth orbit, and they, watch them is all I can say. But my story is supposed to be about volatiles. So to talk about the volatiles, everyone knows, because we've all hammered into our students probably for decades from the textbooks, that the moon is dry. And the standard model explains that the moon was produced in this giant impact on the Earth, partly melted bits of the Earth, but it melted the impactor. The moon then coalesced with enough heat still left to have a nice deep magma ocean. Whatever was present from the original formation of these bodies from the moon would have been lost during this period. It was just gone. And the early 70s, a severely devolatilized moon was the conclusion. We understood it. And then quietly, lunar scientists have been changing the picture. And then it's been accelerating away. So anyone who formed their opinions in this era is probably now being relatively left behind. One thing is you can look at the samples these days and reanalyze them. And so one of the interesting things from my viewpoint is if the moon was dry, did anything arrive later? Well, it's not just theories. People have been increasingly finding evidence for material accreting to the moon since its formation. Just in the last decade, there have been several people reporting that they can look at samples and they can find an individual grain or clast in their sample from, say, the moon, but it could be from a meteorite or from a return sample, that there are materials which are clearly not lunar in origin. So there is now relatively well-established evidence for this, including this paper by Day, which said that they're saying it's a chondritic impactor, so we can start to pin down the nature of the impactors. By the way, low speed and oblique, these are important to reduce the shock and the heating the samples suffer, because that will increase the fraction of the sample which is going to be in a relatively intact state and yet remain on the moon. And more recently, Katie Joy, who's now at Manchester, but in a single paper reported 30 fragments in a single analysis of material which was delivered to the moon after its formation. So that was a very impressive result, and because by aging it from the sample, they were able to say, we can look at these very old samples and then try and compare them to young samples and try and see what's changed. But recently we keep hearing the mantra, follow the water. We've heard it again today. And so if we now just go and think about the moon itself and apply modern, and modern is always a moving target. There's a famous American, Tom Wolfe, who said you never call a movement the new whatever, because pretty soon it ain't. Well, it's just time, isn't it? But with current analysis techniques, you can look in a whole range of lunar materials and find evidence for water. So what we thought of as being dry, we can quantify what we mean by dry, and the range of the estimates is that when we say less than 100, they usually mean 50, 60 parts per million, but up to 350 parts per million. And there's reports in Science from 2006 of over 1,000 parts per million in some samples. These samples in these cases would have been delivered to the moon earlier in the lunar history, but would have added water to this lunar magma ocean soon after it was formed. So we've got moisture and other materials potentially trapped in there. And based on the D to H ratios, people report that this should have been from carbonaceous chondrites. So we're seeing a recurrent picture that material is being delivered to the moon, independent of how the moon itself was formed. There has been an influx since, which we would have sort of all expected, and we can now find the evidence for it. There is still a flux of small particles a day, of course, because material is arriving continuously at the Earth, material is arriving continuously at the moon, and there's a paper which is just out in Icarus which discusses this, how much material is arriving, what is it, where is its origin, and therefore what is being delivered to the moon. The flux of slightly larger objects, these could be maybe a few meters across, can actually be tracked these days because now for over a decade people have been observing lunar light flashes. And when I started, I went to a meeting many years ago and didn't quite get slapped in the face for daring to suggest we could do this, but I was put in my place. There were no lunar light impact flashes, but of course now we know that there are. But from the flash on the surface of the moon, you can see the observation of an impact, you can get the timing, and you can try and tell something about the mass distribution of the objects, because unfortunately, of course, we don't quite know the impact speed of these objects, just the distribution of those impact speeds. But you can at least get a frequency of how much material is being delivered and a mass distribution of that material. So you can start now and this is just a paper that's recently been discussing what those current rates are and what the mass distributions are based on a decade's worth of observations. So we can now start to say what material is arriving at the moon with what sort of speed and what sort of frequency. And it is clear that some of these objects are in effect water-rich or volatile-rich. They have been delivered to the moon, and, oh, wait a minute, maybe there's also a source which actually creates water on the moon. This was a rival theory that if you're going to find any material on the moon, OH or H2O, it might not have been delivered. And so the solar wind itself is continually impacting the moon, and it is continually, therefore, creating, potentially, via hydrogen ion implantation, a thin surface layer which will be moisture-rich. People argue about whether it's stable and will it migrate. So stability is discussed, and migration from one place on the moon to the other is simply because you heat and cool relative surfaces, material will move. But this is a very, very thin surface layer. But it would be water rather than any other volatile, or OH. So if we now got two potential sources, what happens when we look? Well, the spacecraft that have been going, we probably sat through talks where people have given their individual results, but I say it is worth standing back a little and looking at the accumulation of them. But the Indian probe, which had, of course, instruments from a wide range of sources, they were able to show maps which indicate absorption features for the presence of OH or H2O across large areas of the moon. So the idea that the moon is so dry that it is dry is clearly not there, but they were measuring up to 770 parts per million, quite widespread. We can imagine it escaping when the surface gets a bit hot and binding again when it gets a bit cooler, and in the process migrating and ending up at the coldest place. And if you remember the start of my talk, we've got these permanently dark regions at the poles, so we might well imagine looking there. Sunshine reports, this of course is the author, that's my spelling mistake, reported in Science roughly the same time from epoxy, which was deliberately timed to look at the moon to coincide with the Chandrayaan mission, that they also saw OH and H2O, and therein lies again, it's widespread. They were thinking, oh, it's driven by the solar wind because they could see a temporal variation. They found the greatest concentration of the North Pole, but they were setting a limit 0.3 to 0.5% by weight in the lunar soil. Hence these famous things of only we can go there, we can get lots of water. But of course we're looking at probably the surface, so the bulk in the interior is still different. And of course the cold traps are there because we've known since about 2001 from the Lunar Prospector, just by looking at the neutron flux, that there is probably ice, and this data keeps seeming to be reanalyzed every few years as to how much ice, and is it buried how far down, how much material is above it. But it suggested that perhaps below about a 10 centimeter thickness of drier surface material, there is ice in these permanently shadowed regions, and the South Pole was felt to be more interesting. So now we have the North and South Poles of interest, so it's no surprise that L-Cross just a few years ago, this American NASA craft, was aimed at the moon, at the South Pole, to impact in a permanently shadowed region, and then look at the plume that was ejected, to try and study from that plume what the amount of various materials were. And so again, just a couple of years ago now, we're seeing estimates of around 5% by weight of the material that's being ejected from that particular site as being water ice. And there we can also say, because they found hydrocarbons, not just water ice and CO2, that this isn't consistent with a solar wind origin for this material. So this is material which would have been delivered from other sources, from this bombardment. So we've got more than just water, and it's coming from bombardment. So that suggests we've got inputs via impacts, and comets or asteroids, because of course the flux of asteroids is held to be much greater than that of comets. So although we think of comets as wet and the asteroids are relatively dry, the asteroids themselves, of course, have got hydrated materials, and they can be delivering more simply because there's more of them hitting. When you try and do the modelling, and recent modelling from Ong et al. And Stewart et al. Does suggest that if you do simulations, you will find 3 to 6% of high-speed impactors surviving and being distributed on the lunar surface. And if you then model the impact flux rates over, say, a gig a year, you can explain the predicted volumes of water ice at the poles from this source. And I say Ong suggests that asteroid impacts would deliver 6 times as much of the water as comets. So don't just think comets hitting the moon as being delivering hydrated material and water. So we can have schematics where we have maybe a thin upper surface, and this is not to any sort of scale here, highly nonlinear from a solar wind. We have meteoroids almost continually. Ancient bombardment, maybe it was a bit more intense, and there's still debate. That's why people would like to revisit the moon to try and pin down the history of this bombardment. But in between, there's still maybe periodic from the various meteor streams, and also the occasional large impact still. And what we've also got, as I say, is this timescale. Solar wind is constant in effect. We've got regular and then large episodic, and then as you make the larger bombardment, it's rare. And then we've got the ancient material, and we have it, as I say, probably migrating towards the poles. So are there volatiles in comets? So we try and put the next part of our talk together. Well, we have just had been talk this morning. We were talking about stardust, mostly in the next room. And of course, one of the bad messages was stardust is proving very difficult to find the organic content of various samples because of the way it collected it, I'm afraid. But there is plenty of evidence that there is indeed ice and a whole variety of volatile materials on comets. Deep Impact visited Temple 1, for example, and Rosetta will revolutionize what we know about the contents of comets when it gets there later this year and lands on the surface. So pretty soon we'll have quite a large and probably fairly accurate inventory of the contents of the surface of one comet, Churyumov-Gerasimenko. As it turns out, comets, of course, are highly different depending which one you look at. But we will start to be able to work out what it is that's potentially being delivered to the moon. But we have to ask, will all this material being delivered survive the impact process on the moon itself? Relying on these computer hydrocode models, which other people have done previously, might allow you to work at any size scale and any velocity you want, but you're still then relying on putting some assumptions in about what survives what. So here, water is probably easy to model because water is pretty simple. It's water or it's H2O and it likes to recombine. But other volatile materials, and especially the more complex organics, if you deliver those, if we sort of blur volatiles, water, and complex organics, they're not as likely to survive impacts. They can be more complex they are, the less likely they are to survive. So delivery in this case is not really going to be equal to survival because you may have broken things down into more basic forms. And at this stage, you could go back to your hydrocode, you could try calculating shock pressures and the temperatures and the durations and look at the outcomes, but you're plugging in an awful lot of extrapolated material from sources which is usually taking up much higher temperature for longer durations, and then you're plugging in different temperature regimes for much shorter durations and assuming the outcomes can be extrapolated. So there are other people like me who say, well, just go and try it in the laboratory. And yes, you can use this modelling, and you will end up using it again at the end. But at the University of Kent, for example, we can fire materials at speeds of 6 or 7 kilometres a second, not quite the full regime we want to hit the moon, because you might want to go up to 70 kilometres. But we can now develop in our gun, we have a process whereby we can fire frozen materials at these speeds. So this is a new development of the last year or two. So we can take our frozen material, fire it at a target, and see what survives. Here is a picture of the light gas gun at Kent. This is a refrigerator unit down here. We freeze this end of the gun and we place inside it a projectile which is called the sabot, which we drill out and place inside it a plug of frozen material, which is then fired down to this target chamber at the far end. We then recover the target material and we can try and measure what was here and see if any of it is transferred to our target. We often use targets of water, so here's a bag of water, and you might think, why are you using water? The moon isn't that wet. But it turns out, of course, if you deliver something here, it will mix throughout the whole of your sample. You can take a bit of it, and then you can get the concentration, so you can make an absolute measurement for that. We also fire ice. Here's literally a bucket of ice, which we're about to close the door, put in the gun. We can get a crater in the middle and see how much will be delivered to an icy body, such as an icy satellite of an outer planet. Here is sand, which would be our lunar surface. If we had lots of lunar regolith, we'd always use the simulated lunar regolith, but we ration that out because it's very, not real lunar regolith, it's just simulated stuff that NASA produces, but it's still rare. Pre-shot, we have grains in the sand, which are typically, this is 1,000 micron scale bar semi-rounded grains. Post-shot, that's 100 microns, and that's a 25 micron scale bar. We smash the sand up so we know we're impacting it, but This is called system mechanical action. We can then look at the grains in mass spectrometry and see what we find. Here is a hydrocode simulation of one of those sabots I mentioned just sliced in half. Here is the ice about to be fired into water, just about to hit it, and we put tracer points throughout this to establish what the shock pressure history and the regime of the temperature was. So here we've now switched to the hydrocode simulations. These are now contours of pressure. Here is the icy plug region, and it was pretty uniformly shocked, and here is one of our gauge points, and that just happened to be conveniently where we're getting an excursion in pressure which was going higher, but we can see what the bulk of our sample happened to the frozen sample and what the temperature, what the pressure and the duration of that was. So we see the peak pressure, for example, in a gauge point, and we can get the pressure history. And this will be important when we try and model what happens at any other scale. Just some results. Here, firing at water just about 2 kilometers a second. We fired anthracene, stearic acid, and DMSO, which is dimethyl sulfoxide, which is actually used to solvate everything. This was in our target before shot. This is the concentrations, and this is a log scale with a massive jump in concentrations. We successfully transfer material to the target in an impact, and some of it, anthracene, stearic acid, and the DMSO itself, they've survived. The analysis subsequently found them in the same form as previously. So that's quite good. This is a similar shot, but just the DMSO into water, and the peak shock pressure about 2.25 gigapascals, not that great. But here we quantified things, and we were finding survival of around 44% of the complex organic material, in this case the DMSO, that we were firing. So we're demonstrating you can now, in the laboratory, understand the survival in impacts. Here is what happens when we fire at the sand target. Here we got both the target crater and we've got ejector we collected afterwards. We can find elevated samples, so we don't just take from the original target material, we find it elevated in the ejector as well as in the crater. So even when you impact, as you spread your ejector around from the crater excavation, you will still be shedding material from your projectile around the lunar surface, or in this case around our gun. Here's an ice target where again we're finding elevated afterwards. This one was an elevated pre-shot because it turned out DMSO gets everywhere and our water was pure, but when we froze it into ice, our ice maker wasn't pure, but it still showed elevated in the ice crater afterwards by several orders of magnitude. So there's interesting things to do to go up from 2 to 4 to 6 to 7 kilometers a second, look at the range of complex molecules we can use, the volatiles we use, and quantify survival at a range of shock pressures and durations. Then input that into the hydrocode modeling of these large impacts on the moon. At that stage, we'll now be trying to see what survival is. We can plug in delivery rates and be a bit better than the previous assumptions. We can combine it then with what we will know over the next year of increased accuracy about cometary compositions, at least for one comet. And we can, at that stage, just have to simulate the migration across the lunar surface, and we should be able to have a good handle on how much material and what types of material you expect to find in those cold traps at the lunar poles. So I've started off hopefully by trying to persuade you that the moon isn't quite as dry as we might have thought a few years ago. Hopefully, having persuaded you that, I've now shown you a snapshot of how in about another year or so we should be able to understand, we will hope, how that material has been delivered to the moon, how it's migrated across the lunar surface, and what you'd expect to find in those cold traps. And then we just need our astronaut to go dig it up, purify it, and drink it, and waste it all. Thank you.
Questions or comments? Steve Short.
Just next to the moon, there's a very wet object, namely the Earth, and there is, some belief that, and I'm not an expert, that a lot of the water on the Earth had to come from somewhere else, perhaps delivered by comets. That's one of the objectives of Rosetta. Is there some cross-fertilization between looking to see what happened on the moon and looking to see, what's consistent with the amount of water you have on the Earth?
Well, I could almost have planted the question, because of course what I didn't write is one of the reasons we like the moon, those of us who like it, is it's a very good laboratory for long-term processes in this vicinity. Whereas if you look on the Earth, everything gets modified by almost everything else all the time. The moon is a much more stable platform to accumulate these materials. So if we understand the moon, we will have understood an awful lot more about what has happened to the Earth during its history, by inference, because it's in the same neighborhood where a lot of similar processes are occurring, even if today it's a lot harder on Earth to find all these materials preserved without subsequent modification. So we will look at the moon in order to understand what's going here. That is one of the objectives. Although I have to do say, looking at the D to H ratios, depending where on Earth you look, they've been blurred, they're in the deep interior. How do we get to the deep interior? These are still difficult questions even for the Earth. But we will learn a bit more about the moon, I hope.
If I understood your answer, it was no.
Well, yes, that's a fair summary,
yeah.
but we will have made an advance.
Yeah,
Yes.
okay. Any other questions? Okay. Right, thank you very much indeed.